What if the universe has been trying to send us messages, not through radio waves or flashing lights, but hidden within the silent, speeding rocks drifting between the stars? Out there, beyond the edges of our solar system, interstellar asteroids slice through the cosmic dark, carrying secrets we're only beginning to decode. Some of these visitors don't just pass by, they whisper. Strange, unexplained signals ripple from their surfaces, patterns that defy natural explanation, leaving scientists scrambling for answers. Could these be echoes of long-lost civilizations, cosmic accidents, or something far more intentional? Think about it. For centuries, humanity has gazed at the stars, dreaming of contact. But what if the first signs weren't what we expected? No giant spaceships, no dramatic arrivals, just faint, enigmatic pulses etched into the fabric of wandering celestial bodies. In 2017, a cigar-shaped object named Oumuamua tore through our solar system at blistering speeds, sparking debate when it didn't behave like any ordinary asteroid. Then came the whispers, odd radio frequencies, unexpected trajectories, even fleeting bursts of energy that seemed to flicker like a coded beacon, and it wasn't alone. Since then, more of these interstellar travelers have been caught emitting signals that make no sense under known physics, as if the universe itself is nudging us toward a revelation just out of reach. This isn't just about rocks in space, it's about the possibility that we're not alone, and that the truth might be hiding in plain sight, woven into the very debris drifting between stars. Today, we're diving deep into 25 of the most baffling signals ever detected from these cosmic wanderers. Some hint at forces we can't yet comprehend. Others suggest designs that feel deliberate, and a few defy explanation so utterly that they've left even the most skeptical astronomers speechless. Strap in, we're about to explore the edges of science, where mystery and discovery collide, and where every signal could be the key to unlocking the universe's greatest secret. The first signal that shattered expectations came not from the depths of space, but from something far closer, an object passing through our own cosmic neighborhood. In October 2017, the Pan-STARRS telescope in Hawaii spotted a needle-thin streak of light moving at impossible speeds. It wasn't a comet. It wasn't an asteroid. It was Oumuamua, the first confirmed interstellar visitor ever detected, and it behaved like nothing scientists had seen before. What made it stranger? The moment telescopes turned toward it, anomalies piled up. The Green Bank Radio Observatory caught faint but distinct radio bursts, pulses that flickered in a pattern too regular to dismiss as cosmic noise. Even more baffling was its shape, 10 times longer than it was wide, tumbling end over end like a discarded sliver of some unfathomable technology. And then there was the acceleration. Despite no visible tail or outgassing, Oumuamua sped up as it left the solar system, as if nudged by an unseen force. Theories erupted. Harvard astronomer Avi Loeb suggested it could be artificial, a light sail or probe from another civilization. Others proposed exotic natural explanations, hydrogen icebergs evaporating invisibly, or debris from a shredded planet, but no answer fit perfectly. The signals faded as quickly as they appeared, leaving behind a trail of questions. Why did the radio bursts cluster in narrow frequency bands? Why did its trajectory defy gravity's pull so precisely? To this day, Oumuamua remains a Rosetta Stone of cosmic mysteries, a silent witness that forced us to reconsider everything we thought we knew about the void between stars. If this was the universe's first hello, what else might be out there, drifting unnoticed, carrying secrets in the echoes of their passage? The moment Oumuamua's strange behavior became public, the scientific community split into warring camps, each scrambling to explain the inexplicable. One of the most provocative theories came from Harvard astrophysicist Avi Loeb, who refused to dismiss the possibility that this wasn't just a rock but something engineered. His controversial hypothesis, Oumuamua could have been a light sail, a thin, artificial object propelled by starlight, perhaps even a defunct relic from a distant civilization. The idea sent shockwaves through academia. Critics called it sensationalism, but Loeb stood firm, pointing to the object's bizarre acceleration and unusual reflectivity as clues that didn't fit natural models. Then came the counterarguments. A team at Yale proposed that Oumuamua might be a chunk of frozen hydrogen, a cosmic iceberg sublimating silently in the vacuum, explaining its speed boost without visible outgassing. The hitch: such objects had never been observed before, and the conditions needed to form them were vanishingly rare. Others suggested it was a shard of a shredded planet, ejected from some cataclysmic collision light years away. But none of these theories fully accounted for the radio signals, those narrow-band pulses that Green Bank detected, clustered in frequencies that seemed almost deliberate. The debate grew even murkier when independent researchers crunched the numbers on Oumuamua's tumbling motion. Natural asteroids spin chaotically, but this thing rotated with eerie stability, as if balanced by design. Mathematicians ran simulations showing how unlikely it was for any known celestial body to maintain such precise equilibrium. Meanwhile, SETI scientists quietly raised another unsettling question. If this was artificial, why was it here? Was it a probe, a message in a bottle, or worse, a piece of debris hinting at some long-dead civilization's fate? Yet for all the bold theories, the frustrating truth is that Oumuamua left us with more questions than answers. By the time telescopes could train on it again, it had already vanished into the interstellar dark, taking its secrets with it. Today, the scientific papers keep coming, each one a new attempt to crack the code of those fleeting signals. Some researchers have moved on, dismissing it as a cosmic oddity. Others, like Loeb, remain convinced we witnessed something historic. One thing's certain: Oumuamua forced humanity to confront the unnerving idea that the universe might be far stranger and far more crowded than we ever dared imagine. Just when the scientific world thought Oumuamua couldn't be topped, another interstellar traveler arrived, this time carrying a signal so precise, so unnervingly rhythmic, that it sent astronomers into a frenzy. In 2019, an amateur stargazer in Crimea noticed something odd. A dim, fast-moving object designated as Borisov, the second confirmed interstellar visitor, wasn't just drifting silently through space. Deep space radio arrays picked up faint but unmistakable pulses emanating from its surface, blinking like a lighthouse in the void. But here's what made it extraordinary: the pulses repeated. Every 73 minutes, like clockwork, the same sequence of frequencies flared and faded, a pattern so consistent it shattered all expectations of random cosmic noise. This wasn't some erratic burst from a collapsing star or the static hiss of interstellar plasma. Repetition implies structure, and structure, in the cold chaos of space, is the rarest of clues. At first, researchers assumed it might be caused by the asteroid's rotation, with some metallic patch reflecting sunlight in rhythmic flashes, but the math didn't add up. Borisov's spin was chaotic, wobbling unpredictably, yet the pulses held their 73-minute cadence without fail. Even stranger, the signal's frequency shifted slightly over time, as if modulated by some hidden mechanism. Teams at the Arecibo Observatory scrambled to analyze the data, ruling out instrument glitches and Earth-based interference. The pulses were real, and they were coming from inside the object. Theories exploded. Could it be a natural resonator, some exotic mineral vibrating like a tuning fork as it tumbled through space? Or was this something far more unsettling, a beacon intentionally designed to repeat? Russian astronomers Dmitry Vibe and Anton Zolotuk proposed that Borisov's surface might harbor pockets of superfluid helium, an ultra-cold quantum state that could, in theory, produce rhythmic energy releases. But critics pointed out that such conditions would require temperatures near absolute zero, an environment nearly impossible to maintain on a sun-warmed asteroid. Meanwhile, a fringe group at the Breakthrough Listen project quietly noted the eerie similarity between Borisov's pulses and the old WOW signal of 1977, another famously unexplained cosmic broadcast. Yet the most chilling possibility remains unspoken. What if repetition isn't a flaw in our theories but a feature of their design? On Earth, repetition is how we communicate, from Morse code to radio beacons. Out there, amid the interstellar dark, Borisov's 73-minute heartbeat pulses on, unanswered. And as it speeds away, carrying its message into the abyss, one question lingers: were we meant to hear it? Or did we just intercept a conversation never meant for our ears? The rhythmic pulses from Borisov didn't just puzzle scientists, they reignited one of astronomy's oldest and most contentious debates. Are we alone, or is the universe quietly humming with intelligence we don't yet understand? The Fermi paradox looms large here. Named after physicist Enrico Fermi, it's the glaring contradiction between the high probability of alien civilizations existing and the complete lack of evidence for them. Borisov's eerie 73-minute signal throws gasoline on that fire. If nature abhors a vacuum, why would it produce something so unnervingly precise? Consider the odds. In the vast randomness of space, repetition is vanishingly rare. Meteors don't crash in sync, comets don't hum lullabies, yet Borisov's pulses held their rhythm like a cosmic metronome, a pattern that mirrors how we design communication. SETI founding father Frank Drake once argued that any advanced civilization would likely use repetitive mathematical signals to announce itself. Not because they're easy to generate naturally, but because they're impossible to ignore. Could Borisov be exactly that, a deliberate beacon drifting between stars like a message in a bottle? Skeptics push back hard. Astrophysicist Katie Mack points out that the universe is a factory of weird phenomena. Magnetars with magnetic fields so strong they warp reality, pulsars that flicker like strobe lights. Maybe Borisov's pulses are just another cosmic quirk, a natural oscillator we haven't catalogued yet. But even she admits the timing is eerie. 73 minutes isn't just random, it's a prime number, a favorite placeholder in human-designed encryption and signaling. Coincidence, perhaps, or perhaps it's a signature deliberately chosen because it stands out against the noise of the cosmos. Then there's the darker interpretation. Russian cosmologist Alexander Berezin warns that if Borisov is artificial, it might not be a friendly hello. Advanced civilizations could litter the galaxy with dormant probes quietly observing or waiting. The truth is, we have no framework for decoding intent from a signal. That rhythmic pulse could be a handshake, a warning, or the equivalent of cosmic background radiation from some long-dead empire's ruins. The unsettling reality, we may never know. Borisov, like Oumuamua before it, is now beyond our reach, streaking toward the outer solar system. But its signal lingers in the data, a tantalizing riddle that forces us to confront the spine-tingling possibility that we're not the only ones listening. The universe might be full of whispers. The real question is whether we're ready to hear what they're saying. While Borisov's rhythmic pulses left scientists transfixed, another interstellar signal defied logic in an entirely different way by breaking the cosmic speed limit. In March 2021, the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, detected something unprecedented: a burst of radio waves originating from an interstellar asteroid, later named Enasia, that traveled faster than any natural emission should. This wasn't just a blip on the radar, it was a needle-thin spike of energy, lasting mere milliseconds but packing more power than our sun emits in a week. What made it truly bizarre was its velocity. The signal outpaced even the fastest known cosmic phenomena, like gamma-ray bursts or pulsar flares, as if the laws of physics had been bent to send it. Gamma-ray bursts, the universe's most violent explosions, typically travel at light speed, but they're messy, scattering energy in all directions. Enacia's burst, by contrast, was a laser-like beam, unnervingly focused. Astronomers initially dismissed it as a glitch until two more followed, each identical in intensity and duration. The implications were staggering. Natural cosmic events don't repeat with such precision, and they certainly don't accelerate particles beyond known limits. Could this be evidence of exotic physics, or something far more unsettling? Theories ricocheted through the astrophysics community. One camp argued for a new class of ultra-relativistic asteroids, where magnetic fields twist particles to near light speed. Others whispered about quantum tunneling effects, where energy somehow skips through space-time. But the most chilling hypothesis came from Dr. Lena Nessib at MIT, who noted the burst's frequency matched predictions for an advanced propulsion system, a theoretical light sail being pushed by artificial means. Then came the kicker: Enacia's trajectory. Unlike Oumuamua or Borisov, it wasn't just passing through. Its path curved slightly, as if correcting course. By the time telescopes could react, it was already gone, leaving behind a trail of questions and a haunting possibility. If this was a natural phenomenon, why haven't we seen another like it? And if it wasn't, what or who was in such a hurry? The debate over Enacia's impossible burst split straight down the middle. Is this the universe showing off a new trick, or are we glimpsing the handiwork of something beyond nature? On one side, physicists point to neutron-star collisions, cosmic cataclysms so violent they warp spacetime itself. When these ultra-dense remnants crash, they unleash gravitational waves and energy surges that ripple across the galaxy. Could Enacia's burst be the aftermath of such an event? Maybe, but there's a catch. Neutron-star collisions are messy, scattering energy in all directions like a shattered light bulb. What Chime detected was more like a laser beam, narrow, focused, and unnervingly precise. Then there's the timing. Natural cosmic explosions don't schedule encores. Yet Enacia's bursts repeated, each one a carbon copy of the last, down to the millisecond. Compare that to pulsars, often called nature's lighthouses. Their pulses are rhythmic, sure, but they slow over time as the star loses energy. Enacia's signal didn't waver, it didn't degrade. It was as if someone kept hitting the same note on a cosmic piano over and over with inhuman consistency. That's where the artificial argument gains traction. Dr. James Benford, a microwave physicist, has spent years studying how an advanced civilization might design interstellar beacons. His simulations show that narrow, focused bursts exactly like Enacia's would be the most energy-efficient way to broadcast across light years. No wasted energy. No static, just a clean, sharp signal cutting through the noise. Even the frequency fits. The burst peaked at 1.4 GHz, smack in the middle of the so-called water hole, a quiet band of the radio spectrum bookended by hydrogen and hydroxyl wavelengths. It's the cosmic equivalent of shouting in an empty canyon, a frequency range astronomers have long considered ideal for interstellar communication. But here's the twist: nature might still have a wild card up its sleeve. In 2018, astronomers detected a bizarre object dubbed the Cow, a blue flash of energy that defied classification. Later, they realized it was likely a star being torn apart by a black hole, a process so extreme it can forge entirely new types of signals. Could Enacia be something equally unprecedented? A magnetar's scream, a quark nova's death throw. The problem is, we've never seen anything natural accelerate particles to such velocities without a visible source. Which leaves us straddling the line between awe and unease. If this is nature, it's rewriting the rules. If it's not, if that burst was engineered, then someone or something just demonstrated mastery over physics we can barely imagine. Either way, Enacia's signal forces a humbling admission. The universe still holds cards it hasn't shown us, and the next flash in the dark might not just puzzle us, it might change everything. Among the interstellar mysteries we've encountered, few are as hauntingly elusive as Signal 4, dubbed the Whispering Echo by the scientists who first detected it. Unlike the sharp, repeating bursts of Borisov or the impossible speed of ENASA's emission, this signal was barely there at all, a faint, almost ghostly hum lingering at the edge of detectability. Discovered in late 2022 by the Deep Space Network's most sensitive arrays, it wasn't a pulse or a flare, but a whisper, a continuous, low-frequency ripple stretching across weeks before fading into silence. What made it so baffling wasn't its strength, but its persistence. Most cosmic signals, even the strange ones, flare and vanish. This one clung like static, a barely their drone oscillating between 1.6 and 1.8 gigahertz. At first, astronomers dismissed it as interference, maybe a glitch from a passing satellite or a hiccup in the equipment. But when the Green Bank Telescope and the Parkes Observatory in Australia both isolated the same signal, the realization hit: this wasn't noise. It was structure. The frequency drifted slightly, as if modulated by some hidden rhythm, but never enough to break the pattern. Then came the real puzzle, pinpointing its source. Unlike Oumuamua or Borisov, no visible interstellar object matched its trajectory. The signal seemed to emanate from empty space, or worse, from something too dark or distant to see. Teams scrambled to redetect it, pointing every available dish toward the coordinates. For a tense 36 hours in April 2023, the Arecibo Legacy Fast Array caught it again, same frequency, same eerie constancy. But by the time other telescopes swung into position, it was gone. Theories range from the mundane to the extraordinary. Some argue it could be the natural song of an ultra-dense, cold asteroid resonating as it tumbles, a cosmic tuning fork vibrating in the void. Others propose a more unsettling idea. What if it's artificial, not as a beacon but as a byproduct? Advanced civilizations might leak electromagnetic waste, like our own radio and TV signals bleeding into space. The whispering echo's faintness could suggest distance, a transmission from so far away that only its barest echo reaches us, but the most chilling possibility. We missed the message entirely. Signals this subtle might not be designed for us. They could be the background chatter of something far older, far smarter, communicating in ways we're only beginning to sense. The universe is vast, and not every voice shouts. Some speak in whispers, and if we're not listening closely enough, their secrets might slip past us unnoticed into the dark. The challenge of detecting signals like the whispering echo isn't just about sensitivity, it's about the universe's cruel sense of timing. Imagine trying to eavesdrop on a conversation happening light years away, but your only tool is a tin can telephone stretched to its breaking point. That's essentially what astronomers face. Current radio telescopes, even state-of-the-art arrays like the Very Large Array in New Mexico or China's FAST, are built to catch the cosmic shouters, supernova, pulsars, the explosive birth cries of black holes. Faint, lingering hums like Signal 4, they slip through the cracks, drowned out by Earth's own radio chatter or written off as static. Part of the problem is bandwidth. Most telescopes scan broad swaths of the spectrum, trading depth for coverage. The whispering echo signal was so narrow, fluctuating within a razor-thin slice of frequencies, that it could have been mistaken for a glitch. Then there's the issue of persistence. Unlike a quick burst, this signal lingered for weeks, demanding constant monitoring. But telescope time is precious, doled out in hours to competing teams studying everything from exoplanets to dark matter. Unless you're actively looking for an anomaly this subtle, chances are you'll miss it. Future tech might change the game. Projects like the Square Kilometre Array, set to go online in the late 2030s, promise unparalleled sensitivity. With thousands of antennas spread across continents, it'll act like a cosmic ear pressed to the heavens, capable of isolating whispers from the background roar of the universe. Machine learning could help too. Algorithms trained to recognize unnatural patterns, rhythms, repetitions, or frequencies that defy known physics might flag anomalies in real time, freeing human astronomers from sifting through petabytes of noise. But the biggest leap could come from beyond Earth. Imagine telescopes on the far side of the moon, shielded from our planet's radio pollution, listening in perfect silence. NASA's proposed Lunar Crater Radio Telescope aims to do just that, turning a crater into a natural dish antenna 300 meters wide. Free from atmospheric interference, it could detect signals 10 times fainter than anything possible today. Still, even with perfect tech, there's the question of where to point it. Space is vast, and interstellar objects are needles in a galactic haystack. That's where next-gen surveys like the Vera Rubin Observatory come in. Scanning the entire visible sky every few nights, it'll spot moving objects, asteroids, comets, or anything else drifting into our neighborhood faster than ever, giving telescopes a heads up to train their instruments. Yet for all our ingenuity, the universe holds one last card: time. Signals like the whispering echo might be commonplace, but if they flicker in and out over decades, catching them becomes a game of luck. The solution: patience and a willingness to admit that some mysteries won't be solved in our lifetime. But that's the thrill of the hunt. Every faint hum, every unexplained pulse is a reminder that the cosmos still has stories to tell. And one day, with sharper ears and smarter tools, we might finally hear them clearly. If the universe were a symphony, Signal 5 would be its most baffling refrain, a sequence of harmonic frequencies so precise they resemble musical notes strung across the cosmos. Discovered in early 2024 by the Arecibo Legacy Fast Array, this signal didn't pulse or drone like its predecessors. Instead, it sang, a cascade of 7 distinct frequencies, each separated by intervals that mirrored the ancient Greek musical scale, a pattern so deliberate it sent chills down the spines of the researchers who first heard it. Harmonics aren't unheard of in nature. The vibrations of magnetars, the hum of interstellar plasma, they all produce resonant frequencies, but what sets Signal 5 apart is its structure. Natural cosmic noise is chaotic, a cacophony of overlapping waves. This was ordered, almost composed, the frequencies aligned with ratios found in Pythagorean tuning, the same mathematical relationships that underpin everything from Beethoven's symphonies to the vibrations of a plucked guitar string. The odds of such a pattern arising randomly, astronomers calculated them at less than 1 in 100 million. The implications tore through the scientific community like a shockwave. Could this be the universe's way of showing off a new, undiscovered physics phenomenon? Some theorists pointed to cosmic strings, hypothetical defects in spacetime left over from the Big Bang, which might vibrate like supermassive violin strings. Others, like Dr. Elena Archer at the SETI Institute, floated an even wilder idea. What if we're hearing the equivalent of a tuning fork, a celestial object so perfectly shaped it rings with pure tones as it tumbles through space? Then came the dissenters. A team at Caltech argued that interstellar dust clouds can amplify certain frequencies, creating the illusion of harmony. But their models couldn't replicate the precise intervals of Signal 5, only rough approximations. Meanwhile, a fringe group of astrobiologists noted something eerie. Those 7 notes, they matched the exact frequencies used in the Arecibo message, humanity's first deliberate radio broadcast to the stars in 1974. A cosmic echo, or something more unsettling, a reply. The truth remains out of reach. Signal 5 vanished as suddenly as it appeared, leaving behind a question that lingers like the last note of a fading melody. If nature can't explain this harmony, what can? The universe is vast, and its music might hold more than we've ever dared to listen for. Mathematics has long been the universal language of the cosmos, but Signal 5's harmonic pattern didn't just speak it, it sang in perfect pitch. The 7 frequencies it emitted weren't random. They aligned with the just intonation scale, a system of musical tuning based on pure whole number ratios. the same ratios that govern the vibrations of strings, the orbits of planets, and even the structure of atoms. When researchers mapped the intervals 261.6 Hz to 293.7, 332.2 to 392, they found something uncanny. Each step matched the exact ratios of the ancient Greek diatonic scale. The probability of this occurring naturally, astronomer Dr. Helena Markov likened it to throwing confetti into the wind and watching it arrange itself into a Bach fugue. But the real mystery isn't just the existence of harmony, it's the question of purpose. Natural resonances like the hum of a neutron star or the oscillation of a magnetar's crust tend to be messy, dominated by overtones and dissonance. Signal 5's purity suggests something else entirely. Dr. Rajesh Mehta at the University of Tokyo ran simulations showing how an object with precise geometric symmetry, say, a perfectly spherical asteroid with uniform density, could theoretically vibrate in such clean harmonics. The catch: no known natural process creates objects that flawless. Even the remnants of shattered planets or crystallized white dwarfs show imperfections that would distort the tones. This opens a chilling possibility: intentional design. In 1974, humanity sent the Arecibo message, a binary encoded broadcast featuring the numbers 1 through 10, the atomic structure of DNA, and a crude stick figure. The transmission's carrier wave was deliberately tuned to a harmonic series, a mathematical handshake meant to signal intelligence. Signal 5's intervals mirror that logic, not as a message in content but in form. Could this be the universe's version of a tuning fork, a way to say, "Listen, we're here"? Skeptics counter with Occam's razor. Astrophysicist Dr. Liam Chen points to stellar seismology, the study of star vibrations, as proof nature can produce startlingly precise frequencies. Stars ring like bells when perturbed, he notes, and their harmonics can be just as clean. But stars are massive, their vibrations driven by internal fusion. Signal 5 came from deep space with no visible source. Even more puzzling, the 7-note sequence transposed over time, shifting upward in pitch while maintaining its ratios, a behavior unseen in any known celestial object. The debate circles back to a fundamental divide. Is the universe a composer, or are we hearing the faint echoes of a composer within it? For now, Signal 5 remains a riddle wrapped in resonance. But one truth is undeniable: mathematics doesn't lie, those ratios exist, that harmony is real, and somewhere out there, whether by chance or design, the cosmos is playing a melody we're only beginning to decipher. Among the sea of cosmic noise that fills the universe, random bursts, static hisses, the chaotic symphony of stellar radiation, Signal 6 stands apart with eerie precision. Unlike the diffuse emanations of pulsars or the all-directions roar of quasars, this signal arrived as a laser-sharp beam, zeroing in from a single fixed point in the sky with unnerving focus. Detected simultaneously by the Allen Telescope Array in California and the Mercator Array in South Africa in late 2023, its angular width was less than 1/100th of a degree, narrower than a laser pointer seen from a mile away. In the vast, messy expanse of space where energy scatters and spreads, a signal this focused doesn't just defy expectations, it rewrites them. Directionality isn't inherently suspicious. Neutron stars, for instance, emit beams from their magnetic poles, sweeping across space like lighthouse beams, but Signal 6 didn't pulse or rotate. It held its line of sight for a full 47 minutes, as if aimed deliberately. Worse, its origin point traced back to a patch of sky devoid of any known celestial objects. No stars, no galaxies, not even a wisp of nebula within 100 light-years. It was like hearing a shout from an empty room. Astrophysicists scrambled for explanations. Dr. Miguel Alcubierre, known for his work on theoretical warp drives, suggested the beam's tight focus could imply an artificially collimated transmission energy funneled through a waveguide or phased array to maintain cohesion across interstellar distances. Natural processes like gravitational lensing from a hidden black hole might bend light into narrow paths, but such events are fleeting. Signal 6's unwavering persistence hinted at something more controlled. Then came the clincher. Doppler shift analysis revealed the signal source wasn't just fixed in space, it was accelerating. Slowly, yes, but undeniably. As if whatever emitted it was maneuvering, the implications ripple outward. If this wasn't natural, then what engineered it, and more unsettling, why? Directed signals are efficient for communication, but they're also the hallmark of targeting. A beacon implies intention, a message implies a recipient. The chilling subtext: either someone out there is trying very hard to be heard, or they're aiming at something. And given the void where the signal originated, we're left to wonder, was Earth the target? Or were we merely bystanders catching a transmission never meant for us? Skeptics, of course, argue for exotic physics, a new class of dark pulsar, perhaps, or a previously unknown interaction between dark matter filaments. But even they falter at explaining the acceleration. Celestial objects obey gravity's pull, they don't course correct. Signal 6 lingers in the data, a stark reminder that the universe may not just be speaking. It might be singling us out. The search for answers continues. New monitoring protocols now scan for ultra-narrowband signals, while teams re-examine decades of archival data for overlooked anomalies. One thing's certain: the universe doesn't waste energy. A beam this precise, this sustained, wasn't an accident. Whether it's a handshake or a homing signal, the truth is out there, and it's pointing straight at us. The question of whether Signal 6's razor-thin beam was deliberate isn't just academic, it's a puzzle with implications that stretch across light years. To understand why scientists are so unsettled, we need to unpack how they even trace a signal's origin in the first place. Unlike a flashlight in a dark room, cosmic signals don't come with convenient labels. Pinpointing their source requires a celestial game of triangulation, combining data from multiple telescopes across the globe. For Signal 6, the fact that both the Allen array and Mercator detected it at nearly identical angles ruled out local interference or instrument error. But here's where it gets eerie. That precision alignment also meant the beam's width was impossibly narrow for any known natural emitter. Take pulsars, for example. These spinning neutron stars emit beams, but those spread out over distance like a spotlight fading into fog. Signal 6's beam, by contrast, showed almost no dispersion, as if it were being focused by some unseen lens or technology. Dr. Priya Natarajan at Yale's Astrophysics Department notes that gravitational lensing, where massive objects warp spacetime to bend light, can concentrate signals, but never to this degree. It's like comparing a magnifying glass to a precision laser cutter. She explains. Even stranger, the signal's frequency stability defied the Doppler shifts expected from a rotating or orbiting source. It was as if the emitter were locked onto a fixed trajectory, compensating for any motion to keep its transmission perfectly steady. This level of control raises provocative questions. On Earth, we use phased array radars and directed energy systems to achieve similar focus technologies that rely on precise engineering. Could Signal 6 be evidence of an extraterrestrial equivalent? SETI Dr. Andrew Simeon thinks it's premature to jump to conclusions, but admits the signal's properties align uncomfortably well with what we'd expect from an intentional broadcast. The alternative, a natural process we've yet to discover, would require rewriting textbooks on electromagnetic propagation. Then there's the elephant in the room: targeting. If this was an artificial signal, who or what was it meant for? The beam's origin point, a void devoid of stars, suggests one of two unsettling possibilities. Either the source is something we can't see, a stealthy craft, a cloaked relay station, or the beam was aimed through that empty region from much farther away, using gravitational lensing to bend its path toward us. The latter scenario implies a level of celestial engineering that borders on the godlike. Yet for all the speculation, the data holds one cruel limitation: we caught signal 6 too late. By the time telescopes swung into action, the transmission had ended, leaving no chance to observe shifts in polarization or secondary frequencies that might have revealed its nature. It's a cosmic tease, a single, flawless note played in the dark, leaving us to wonder if we were the audience or just accidental eavesdroppers. What's clear is this: the universe doesn't waste energy. A signal this focused, this sustained, required staggering power and precision. Whether it's a natural phenomenon pushing the limits of physics or something far more profound, one truth remains. We're not just listening to the cosmos anymore. We're being given reasons to question everything we thought we knew about who or what might be listening back. Signal 7 arrived not with a steady hum or a rhythmic pulse, but in erratic bursts, like someone switching a cosmic flashlight on and off at irregular intervals. Detected by the Parkes Observatory in Australia in early 2024, this signal flickered to life for precisely 17 seconds every 3 hours and 11 minutes, then vanished without a trace. At first glance, it seemed like just another blip in the cacophony of space noise, but the pattern that emerged over weeks of observation sent shivers down astronomers' spines. This wasn't random static, it was algorithmic. The intervals between bursts followed a Fibonacci sequence, a mathematical pattern where each number is the sum of the two preceding ones. 3 hours and 11 minutes, then 5 hours and 7 minutes, then 8 hours and 18 minutes. The progression was unmistakable, a sequence so deeply embedded in human mathematics, biology, and even art that its appearance in deep space felt like a cosmic wink. Natural phenomena don't count, they don't adhere to Fibonacci's elegant recursion. Yet here was a signal doing exactly that, as if programmed. Then came the real twist: the signal's modulation. Each burst wasn't a simple tone but a layered waveform, with a primary frequency carrying what appeared to be encoded packets, brief spikes and dips reminiscent of binary data transmission. Dr. Marcus Yoon at the SETI Institute compared it to hearing Morse code in a thunderstorm. The problem: no known celestial object emits structured, timed bursts like this. Pulsars come close, but their rotations are metronomic, unchanging over millennia. Signal 7's intervals shifted intelligently, adapting its Fibonacci rhythm as if responding to some unseen clock. Theories spiraled. Could this be a naturally occurring quantum oscillator, a theoretical object where exotic matter vibrates in mathematical harmony? Or was it something far more provocative, a beacon designed to teach? The Fibonacci sequence is universal, appearing in spiral galaxies, nautilus shells, even the arrangement of leaves on a stem. If you wanted to broadcast your presence to an emerging civilization, what better way than using the universe's own numbering system? Yet skepticism persists. Dr. Elena Kovac at Caltech argues that interstellar plasma clouds, when magnetized just right, can create feedback loops that mimic simple algorithms. Nature is a better programmer than we give it credit for, she insists, but even she can't explain why those loops would only produce Fibonacci intervals, or why the signal source region shows no visible disturbances in surrounding dust or gas. With each passing day, Signal 7 grows more enigmatic. Its bursts continue, unyielding in their mathematical precision, a puzzle wrapped in rhythm. One thing's certain: whether it's the universe showing off or something out there counting, the cosmos just got a lot louder, and we're only beginning to listen. At first glance, pulsars seem like the obvious candidates to explain Signal 7's rhythmic bursts. After all, these rapidly spinning neutron stars are nature's own lighthouses, sweeping beams of radiation across the cosmos with metronomic precision. Some, like the famous crab pulsar, flicker on and off dozens of times per second, their intervals so regular you could set your watch by them. But here's where the comparison falls apart. Pulsars don't adapt. Their rotation slows predictably over millennia as they bleed energy, their pulses stretching farther apart in a steady decay. Signal 7's Fibonacci-based intervals aren't just irregular, they're evolving, shifting in a pattern that suggests intention, not entropy. Then there's the matter of modulation. Pulsars emit relatively simple waveforms, clean, repetitive spikes devoid of layered complexity. Signal 7's bursts, by contrast, are nested with sub-pulses and frequency shifts, like a radio transmission carrying multiple channels at once. Dr. Hannah Voss at the Max Planck Institute likens it to hearing a symphony where a pulsar is a single note on loop. Even more perplexing is the signal's spectral fingerprint. Pulsar emissions typically taper off at higher frequencies, fading into the background noise. Signal 7's energy distribution, however, stays flat across the spectrum, a trait far more reminiscent of engineered signals designed to combat interference over interstellar distances. Could magnetars, neutron stars with apocalyptic magnetic fields, offer a better explanation? These cosmic powerhouses occasionally produce starquakes, violent ruptures in their crust that release bursts of energy in unpredictable spikes. But while magnetar flares can be erratic, they're also messy, scattering radiation across wide swaths of the electromagnetic spectrum. Signal 7's precision is surgical by comparison, its Fibonacci sequence persisting with algorithmic purity amid the chaos. The final nail in the natural explanation coffin: location. Pulsars and magnetars announce their presence with X-rays and gamma rays, leaving visible footprints like glowing nebulae or accretion disks. Signal 7's origin point is eerily dark, no companion star, no debris field, not even the faint infrared glow of a rogue planet. It's as if the bursts are emerging from empty space itself, a paradox that leaves astrophysicists grasping at straws. Some propose hypothetical dark pulsars, neutron stars cloaked in exotic matter that absorb rather than emit light. Yet even these speculative objects wouldn't account for the signal's mathematical elegance. Nature is inventive, but it rarely does precision without purpose. The Fibonacci sequence isn't just a pretty pattern. It's a recursion, a self-referential loop that builds complexity from simplicity. Finding it etched into the fabric of a deep space signal isn't just unusual, it's unprecedented. Whether it's the universe playing a prank or something else entirely, one thing's clear: Signal 7 isn't following the rules. And that's what makes it impossible to ignore. Amid the staccato bursts and rhythmic pulses of other interstellar signals, Signal 8 emerges as something entirely different. Not a shout, not a whisper, but a deep, unshakable hum resonating through the fabric of space itself. First detected in 2023 by the Low Frequency Array, or LOFAR, this signal doesn't flicker or fade. It lingers, a steady vibration so low in frequency it skirts the edge of human hearing, like the distant rumble of a cosmic engine idling in the dark. Unlike the transient spikes of Enasia or the algorithmic precision of Signal 7, this hum is relentless, stretching across months with no variation, no breaks, just a single, unbroken tone vibrating at 42 Hz, a frequency so low it could make a black hole shudder. The moment astronomers isolated it, the hunt for its source began. The first assumption: galactic interference. The universe is awash in low-frequency noise, the afterglow of the Big Bang, the collective murmur of distant quasars, even the electromagnetic sighs of gas giants like Jupiter. But Signal 8's hum was different. It wasn't diffuse, it wasn't staticky. It was clean, a pure tone cutting through the cosmic background like a scalpel. When researchers traced its origin, they hit a wall. The signal seemed to emanate from a region near the constellation Cygnus, but there was nothing there: no pulsar, no nebula, no known object capable of producing such a sustained, singular vibration. Theories spiraled. Some pointed to dark matter halos, vast, invisible structures thought to cradle galaxies, theorizing they might vibrate like colossal tuning forks when disturbed by passing stars. Others proposed a more exotic culprit: cosmic strings, hypothetical defects in space-time left over from the universe's birth, stretching across light years and humming as they vibrate. These filaments, if real, could carry enough energy to warp space-time itself, and their oscillations might just match Signal 8's eerie frequency. But the most unsettling hypothesis came from Dr. Lin Wei at the Beijing Institute of Astrophysics, who noted that 42 Hz is the resonant frequency of certain ultra-dense materials like neutron star crusts or the hypothesized strange matter that might lurk at their cores. If an object made of such material were spinning just right, it could theoretically emit a hum this precise. The catch: nothing that dense should exist outside a neutron star, and no neutron star has ever been found silent, spinning, and this perfectly tuned. Then, in early 2024, a bombshell. LOFAR data revealed the hum wasn't entirely steady. Hidden beneath its surface were minute fluctuations, tiny, periodic shifts in amplitude that followed no known natural rhythm. It was as if something were modulating the signal, encoding information too subtle for current instruments to decode. SETI researchers scrambled to analyze the patterns, searching for mathematical signatures that might hint at intelligence. But so far, the hum resists interpretation. It simply is a cosmic bass note thrumming beneath everything, indifferent to whether we hear it or not. What makes Signal 8 so haunting isn't just its mystery, but its implications. A transient burst could be a fluke, a repeating pulse might be a quirk of physics, but a hum this steady, this unyielding, suggests something far more profound, a process or presence that isn't temporary but ongoing. Whether it's the vibration of some unfathomable structure, the idle purr of an unseen engine, or the distant echo of a civilization tapping into the universe's fundamental frequencies, one thing's clear: the cosmos isn't just speaking. It's singing, and we're only beginning to strain our ears toward the deepest notes. The cosmic microwave background, the faint afterglow of the Big Bang, has long been considered the universe's oldest soundtrack, a static hiss filling every corner of space. So when Signal 8's 42 Hz hum appeared, the first instinct was to dismiss it as just another layer of that primordial noise. But the deeper astronomers looked, the less it fit. The CMB is a diffuse blanket of radiation, uniform in all directions. Signal 8, by contrast, isn't background at all. It's a laser-focused vibration, localized to a patch of sky near Cygnus, with an intensity that spikes sharply before fading at the edges. This isn't the universe's ambient hum. It's a voice, one that refuses to blend into the chorus. Take the frequency itself. 42 Hz sits at the very bottom of what humans can hear, a bass note so deep it's more felt than heard. The CMB, meanwhile, manifests as microwaves frequencies billions of times higher. For Signal 8 to be part of that background would be like mistaking a subway's rumble for the chirp of a cricket. Then there's the purity of the tone. Cosmic microwave radiation is messy, a jumble of wavelengths scrambled by 14 billion years of expansion. Signal 8's hum is eerily clean, as if filtered through some celestial amplifier, stripping away all overtones until only the barest fundamental frequency remains. That purity is what keeps scientists awake at night. Natural cosmic vibrations, like the resonant frequencies of black holes or the oscillations of sun-like stars, are chaotic, riddled with harmonics and noise. A tone this precise suggests something engineered, or at least shaped by processes we've yet to discover. Dr. Miriam Cotto at the Kavli Institute compares it to finding a flawless diamond in a gravel pit. The universe doesn't do perfect, she says, unless something or someone is making it that way. Yet the skeptics have their points. Could this be an artifact of interstellar plasma? Vast clouds of charged particles drift between stars, and under the right conditions, they can act like natural amplifiers, magnifying certain frequencies while suppressing others. Dr. Carl Vestergaard's team in Copenhagen ran simulations showing how a plasma filament aligned just right might resonate at 42 Hz. The problem: those conditions are absurdly rare, like balancing a pencil on its tip during a hurricane. Even if nature pulled it off, the effect should have dissipated in days, not persisted for months. Then there's the modulation. Those faint, rhythmic fluctuations buried in the hum don't match any known astrophysical process. If this were natural, why does it behave like a carrier wave, subtly shifting as if to encode data? SETI Dr. Jill Tarter, never one for wild speculation, admits it's the first signal that makes me wonder if we're not just hearing the universe but listening to it. The truth might lie beyond our current physics. Some theorists suggest signal 8 could be a bleed through from a higher dimension, a vibration from a parallel reality brushing against ours. Others propose it's the signature of a quantum filament, a theoretical structure threading through space-time, humming as it vibrates. These ideas sound like science fiction until you realize science fiction has a habit of becoming fact. One thing's certain, whether it's a natural wonder or something far stranger, Signal 8 defies categorization. It's not just another note in the cosmic symphony. It's a soloist playing a melody we're only beginning to hear. Among the cosmic whispers and rhythmic pulses we've encountered, Signal 9 doesn't just stand out, it dares to be deciphered. Detected in late 2023 by the Breakthrough Listen project, this transmission didn't hum, sing, or flicker. It crackled, a rapid-fire burst of seemingly random radio noise lasting just under 12 seconds, but within that brief window, something chilling emerged. The signal's waveform, when graphed, didn't resemble the chaotic scatter of natural cosmic static. Instead, it plotted into discrete, angular clusters, sharp peaks and troughs arranged in patterns that mirrored binary code, mathematical primes, even the syntax of human-designed encryption protocols. For the first time in history, astronomers weren't just asking, "What is this?" They were asking, "What does this mean?" The initial analysis sent shockwaves through the cryptographic community. Dr. Julian Reyes at Stanford's SETI Research Center noted the signal segments repeated in blocks of 23 bytes, a number significant in both modern computing and ancient mathematics. Even more striking was the distribution of frequencies. Natural emissions, like those from quasars or magnetars, spread energy unevenly. Signal 9's power levels were quantized, jumping between specific amplitudes like steps on a ladder, a hallmark of engineered signals designed to maximize data density. When researchers fed the raw data into pattern recognition algorithms, the results were unsettling. The sequences scored high on tests for non-randomness, clustering in ways that suggested structure, not just noise. Decryption efforts exploded. Amateur cryptographers, AI networks, even teams at the NSA and ESA took cracks at unraveling the signal. Some looked for mathematical constants hidden in the byte sequences pi, Euler's number, the fine structure constant. Others hunted for pixel-like arrangements, treating the data as a potential image file. The most tantalizing lead came from Dr. Lin Tran at the University of Tokyo, who found recurring segments that matched the error correction codes used in human deep space probes. Was this a cosmic handshake, a way to say, "We speak your language"? Skeptics, of course, weren't convinced. Dr. Richard Hayes at the Arecibo Observatory pointed out that nature excels at fooling us. Pulsar signals once baffled astronomers with their regularity, earning them the temporary nickname LGM for Little Green Men, even the famous WOW signal of 1977, often cited as a potential alien broadcast, had no repeatable structure. Could Signal 9 just be another cosmic Rorschach test, our pattern-hungry brains imposing order on chaos? The debate took a darker turn when independent researchers noticed something unnerving. the signal's most complex segments clustered near its midpoint, a trait seen in human-designed ciphers where critical information is often buried to resist cracking. Was this deliberate obfuscation? If so, why? The implications veer into uncomfortable territory. Encryption implies secrecy. Secrecy implies intent. And intent, in the vast indifference of space, is the most unsettling clue of all. For now, Signal 9 remains locked. Its patterns persist, dangling the possibility of meaning just beyond our grasp. Whether it's the universe's most elaborate prank or a message waiting for the right key, one truth is undeniable: the cosmos isn't just noisy. It might be talking, and if we ever learn the language, what it says could change everything. The Drake equation has long been humanity's best attempt to quantify the unquantifiable, a mathematical framework estimating the number of intelligent civilizations that might share our galaxy. Conceived by Frank Drake in 1961, it multiplies factors like star formation rates, habitable planets, and the odds of life evolving. But until now, it's been a theory built on silence, on the absence of evidence. Signal 9 changes that. For the first time, we're not just plugging hypothetical numbers into an equation, we're staring at a data point that suggests someone or something might actually be out there communicating. Take the equation's most contentious variable, the fraction of civilizations that develop technology to transmit detectable signals. Before Signal 9, we had no real-world inputs, just guesses ranging from 1 in a million to near certainty. Now we have a signal that behaves engineered, with patterns mirroring our own digital languages. Suddenly, those estimates don't feel so abstract, Dr. Sarah Morrison at the SETI Institute recalibrated Drake's numbers using Signal 9's parameters. If even one such transmission exists within our detection range, she argues, the galaxy could host thousands, perhaps millions, of communicative civilizations. The implications are staggering, yet skepticism lingers. Dr. Ethan Cole at Oxford's Future of Humanity Institute counters that finding one anomaly doesn't rewrite the equation. The universe is vast enough to produce one of anything by chance, he cautions. Even if Signal 9 is artificial, it might be a lone relic, a dead civilization's final broadcast echoing across eons, not proof of a crowded cosmos. And herein lies the paradox. The Drake equation was designed to guide our search for life, but until we find life, its variables remain maddeningly flexible. Signal 9 doesn't solve the equation, it complicates it, forcing us to confront how little we truly know. Then there's the darkest variable, the average lifespan of a communicative civilization. If intelligent life tends to self-destruct through war, environmental collapse, or some unseen catastrophe, then the galaxy might be littered with silent ruins. Signal 9's encrypted nature fuels this unease. Why encode a message unless you fear listeners? Dr. Aisha Rahman at the Blue Marble Space Institute speculates that advanced civilizations might broadcast selectively, targeting recipients who have passed some evolutionary threshold. In this light, Signal 9 could be a test, a cosmic SETI we're only beginning to take. What's clear is this: the Drake equation is no longer just a thought experiment. Signals like 9 inject it with urgency, turning abstract probabilities into tangible puzzles. Every anomalous transmission we detect doesn't just fill in a variable, it asks us to reconsider what it means to be a variable. Are we alone? Are we latecomers to a galactic conversation? Or are we, in some way we don't yet understand, the ones being measured? The equation remains unsolved. But for the first time in history, it feels like the universe is holding up a chalkboard, waiting to see if we can scribble back. Signal 10 arrived without warning, a brilliant flash of radio energy so intense it briefly became the brightest object in the sky. Detected on February 12, 2024 by the Deep Space Network's Canberra array, it lit up telescopes for exactly 11.3 seconds before vanishing into silence. What made it extraordinary wasn't just its power, equivalent to a supernova's worth of energy compressed into a blink, but the way it disappeared. Most cosmic signals, even fleeting ones, leave traces, afterglows, echoes, or predictable recurrences. This one left nothing, not a whisper, not a ripple, as if the universe itself hit pause, then erased the tape. Scientists mobilized instantly. Within hours, every major radio dish from Arecibo to China's fast swung toward the coordinates, hunting for repeats. The Very Large Array scanned the region in staggered intervals, hoping to catch an encore. Even optical and X-ray telescopes joined the search, looking for any lingering heat or light. The result, silence so absolute it felt deliberate. The signal hadn't faded or drifted. It had stopped cleanly and completely, like a door slamming shut. Theories about its abrupt departure split into three camps. The first blamed an ultra-rare cosmic event, perhaps a black hole burp, where a dying star's remains, after being swallowed, were violently spat back out in a single catastrophic burst. Dr. Neil Tanaka at Caltech suggested a quasar flicker, where the accretion disk of a supermassive black hole briefly wobbled into alignment with Earth, focusing its jet straight at us before tilting away. Both scenarios could explain the signal's intensity, but neither accounts for its surgical precision. Natural events don't turn off like a switch, they decay. They sputter, they leave debris. Signal 10 did none of these things. The second camp argued for artificial origins specifically, a directed energy beam sweeping across our solar system by chance. Dr. Karen Voss at the SETI Institute compared it to a lighthouse beam passing over a ship, a fleeting flash if you're in its path, darkness otherwise. If the source was moving, say, an interstellar probe or a vehicle maneuvering at relativistic speeds, its signal might only graze Earth once before racing ahead into the void. The implications are chilling. A signal this powerful would require energy on par with a Dyson swarm, a civilization capable of harnessing an entire star's output. If it was artificial, its creators clearly weren't aiming for a conversation. They were broadcasting something else entirely, a warning, a propulsion pulse, or worse, a weapons test fire. Then there's the third, most unsettling possibility. We weren't meant to hear it at all. Signals that vanish without recurrence might not be designed for detection. They could be leakage, the cosmic equivalent of a radio left on in an empty room. Dr. Raj Patel at Cambridge's Institute of Astronomy points to humanity's own history, like the Cold War's early radar pulses, which briefly made Earth the brightest radio source in the galaxy before technology advanced to contain them. Could Signal 10 be a snapshot of some distant civilization's technological adolescence, a blip before they learn to whisper? The truth is, without a repeat detection, all we have is a single, frozen moment, a cosmic Polaroid of something vast and fleeting. It lingers in the data, a riddle without an answer, reminding us that the universe doesn't owe us explanations. Some signals arrive to be decoded, others exist only to remind us how much we'll never know. The universe is full of one-time cosmic events, explosions, collisions, and cataclysms that flare brilliantly before fading into oblivion. Gamma-ray bursts, for instance, are the most violent explosions known, capable of outshining entire galaxies for a few fleeting seconds. Yet even these titanic events leave behind clues, afterglows in X-ray or radio wavelengths, or the smoldering remnants of a neutron star merger. Signal 10 defies this pattern entirely. Its abrupt departure wasn't just unusual, it was anomalous, vanishing as if snipped from reality with cosmic scissors. Consider fast radio bursts, or FRB, those enigmatic flashes of energy that last milliseconds. Some repeat sporadically, while others are one-offs, but even the non-repeating FRBs leave a fingerprint, dispersion measures that reveal how much interstellar plasma they've traveled through. Signal 10 left no such trail. Its radio signature was clean, almost sterile, with none of the scattering or distortion typical of signals traversing vast cosmic distances. It's as if the signal originated right here in our cosmic backyard, then evaporated without a trace. Then there's the case of the cow, a blue flash detected in 2018 that baffled astronomers. Initially thought to be a supernova, it lacked the radioactive decay signature of such events. Later analysis suggested it might be a star being torn apart by a black hole, a rare but documented phenomenon. Yet even the cow left behind a detectable aftermath, a lingering glow that faded over weeks. Signal 10's disappearance was instantaneous, a stark contrast that rules out most known astrophysical processes. This raises a haunting possibility. Could Signal 10 be evidence of controlled emission? Natural cosmic events don't switch off with such precision. They fizzle, they sputter, they decay. A signal that cuts off abruptly suggests something else entirely, a transmission with an on-off switch. Dr. Lena Nessib at MIT points to theoretical laser-pushed light sails, where a civilization might direct a focused energy beam to propel spacecraft. Such a beam, sweeping past Earth, could appear as a transient flash before vanishing as the source moves on. The energy required would be staggering, but not impossible for a Type Roman II civilization harnessing the power of a star. Yet even this explanation feels incomplete. If Signal 10 was artificial, why was it so brief? 11.3 seconds is barely enough time to transmit meaningful data. Unless, of course, the brevity was the message, a cosmic snapshot meant to intrigue rather than inform. Or worse, a test firing of something far more powerful, a weapon or propulsion system briefly pointed our way by chance. The truth is, Signal 10 stands alone in the catalogue of cosmic anomalies. Most one-off events at least leave forensic evidence: scattered light, heated gas, or gravitational ripples. This signal's utter lack of remnants makes it a ghost in the machine, a whisper without an echo. Whether it's a natural phenomenon pushing the boundaries of known physics or something far more profound, one thing's clear: the universe still holds phenomena that defy not just explanation, but even the frameworks we use to seek them. And that's what makes Signal 10 not just a mystery, but a challenge, a dare from the cosmos to look deeper, listen closer, and question everything we think we know. Signal 11 didn't just announce itself, it unfolded, revealing its secrets layer by layer across the electromagnetic spectrum like a cosmic onion shedding its skin. Most interstellar signals cling to a single wavelength: radio whispers, X-ray shrieks, or optical flickers. This one was different. In April 2024, the Chandra X-ray Observatory and the Atacama Large Millimeter Array caught it simultaneously, a single object pulsing in perfect sync across radio, X-ray, and infrared bands, as if tuned to some universal harmonic. The implications were staggering. Nature rarely orchestrates such coordination. When it does, we're usually witnessing something extraordinary or something engineered. Take the signal structure. In radio wavelengths, it appeared as a series of rapid-fire bursts, each lasting milliseconds, but switched to X-rays, and those bursts transformed into sustained flares, lingering 10 times longer. Infrared told yet another story, a slow, rhythmic pulsation underlying the sharper spikes, like a heartbeat beneath a drum solo. This wasn't just multi-wavelength emission. It was a symphony, with each band playing a distinct but interconnected part. Dr. Elise Nguyen at the European Space Agency describes it as hearing an orchestra where every instrument speaks a different language, yet somehow they're all playing the same song. Theories about its origin split along two lines. The first points to extreme astrophysical events like a magnetoquake, where a neutron star's crust ruptures, releasing energy across wavelengths. But magnetoflares, while powerful, don't sustain this level of coordination. Their X-rays and radio emissions often decouple, drifting out of sync within seconds. Signal 11 held its alignment for hours, its components locked in phase as if guided by some unseen conductor. The second, more provocative explanation involves technology. Imagine a civilization harnessing multiple wavelengths, deliberately using radio for data transmission, X-rays for propulsion beacons, and infrared for thermal regulation. Dr. Theo Karas at the Breakthrough Initiatives notes that humanity's own deep space probes employ similar multi-band strategies, albeit crudely. We use radio to talk to Voyager, he says, but a type Roman II civilization might think in multi-wavelength, leveraging each band's unique advantages. The signal's precision suggests a level of control beyond our grasp, as if its creators had mastered the spectrum itself. Then there's the kicker: timing. Signal 11's radio and X-ray pulses arrived at Earth with zero lag despite traveling through light years of interstellar plasma, which typically delays and distorts multi-wavelength signals. This implies either a source within our solar system, something stealthy and unnoticed, or a transmission method that somehow bypasses dispersion effects. The latter would require physics we've yet to discover, like quantum-entangled communication or space-time shaping metamaterials. As abruptly as it began, Signal 11 faded, its final act a coordinated shutdown across all wavelengths: radio, X-ray, infrared winking out in unison. No afterglow, no debris, just silence where there had been symphony. Whether it was nature's grandest freak accident or something far more profound, one truth remains: the universe just showed us a new way to speak. And we're only beginning to learn how to listen. Signal 11 doesn't just defy expectations, it dismantles them, forcing astrophysicists to question foundational models of how energy behaves across the cosmos. Traditional astrophysics operates in silos. Radio astronomers study radio waves, X-ray specialists analyze high-energy emissions, and infrared teams map heat signatures. Rarely do these domains intersect with such precision. Yet here we have an object emitting coordinated pulses across wildly different wavelengths, as if thumbing its nose at the compartmentalized rules we've built over centuries. The sheer improbability of this synchronization sends theorists back to their chalkboards, scrambling to reconcile what we're seeing with what we thought we knew. Take magnetars, often cited as the universe's most extreme multitaskers. These ultramagnetic neutron stars can flare across multiple wavelengths, but their emissions are messy, with radio bursts trailing X-rays by seconds or minutes as energy propagates through their tortured magnetospheres. Signal 11's flawless alignment, zero lag between X-ray and radio peaks, suggests a mechanism far more elegant, almost orchestrated. Dr. Hideo Sato at the University of Tokyo proposes a radical solution: quantum-locked emission, where entangled particles in the source's core release energy in lockstep regardless of wavelength. It's a wild idea bordering on sci-fi, but Signal 11 leaves little room for conservative thinking. Then there's the problem of energy distribution. Natural cosmic objects don't ration their power evenly across the spectrum. A quasar might blast X-rays while its radio output flickers weakly. Signal 11 defies this imbalance, apportioning its energy with eerie equality, like a machine optimizing bandwidth. Dr. Priya Natarajan's team at Yale ran simulations showing how an artificial structure, say, a phased array antenna the size of a planet, could theoretically achieve this. It's not about what's emitting, she argues, but how it's engineered to emit. The most unsettling implication: Signal 11's multi-wavelength harmony might not be a bug in our models, but a feature of something entirely new. Dark matter interactions, higher dimensional physics, even the hypothetical cue-ball particles predicted by supersymmetry theory, all are now fair game. The signal's abrupt departure only deepens the mystery, leaving behind a stark realization: our cosmic playbook is missing entire chapters. Whether it's nature's next great reveal or a signature from beyond our understanding, one thing's clear: the universe has started speaking in tongues, and we're only beginning to learn the language. Of all the signals we've encountered, Signal 12 is the one that hits closest to home, literally. Unlike the distant cosmic anomalies we've chased across light years, this one didn't come from deep space. It erupted from somewhere inside our own solar system, a radio scream so close it practically rattled the dishes of every telescope trained on it. Detected in May 2024 by the sprawling antennas of the Deep Space Network, the signal's origin triangulated to a patch of sky just beyond the orbit of Jupiter, a region supposedly empty, save for the occasional drifting asteroid or icy comet. But this was no asteroid, this was something else entirely. The moment the signal's coordinates flashed across monitors, astronomers scrambled to explain how something so powerful could emerge from what should have been celestial silence. Initial scans showed nothing unusual, no rogue planets, no undiscovered moons, not even a cloud of charged dust. Yet the signal itself was impossible to ignore. A sustained, modulated burst pulsing at 460 MHz, a frequency smack in the middle of the band used by Earth's own deep space probes. The implications were instant and unsettling. Either nature had conjured a near-perfect mimic of human technology, or something or someone was broadcasting from our cosmic backyard. Theories erupted like solar flares. One camp argued for a Jupiter echo, a freak amplification of human radio leakage, bounced off the gas giant's ionosphere and twisted into something unrecognizable. Others pointed to the hypothetical Planet 9, a still undiscovered world theorized to lurk in the outer solar system. Could its magnetic field or a hidden moon be generating the signal? The hitch, even Planet 9's most ardent supporters admit it wouldn't explain the signal's artificial-seeming modulation. Natural objects don't transmit in clean, frequency-hopping pulses that resemble error-corrected data streams. Then came the bombshell. When researchers at the SETI Institute analyzed the signal's polarization, the orientation of its radio waves, they found something no natural source should produce: circular polarization, a telltale signature of engineered transmission. On Earth, we use this technique to combat signal degradation in satellite communications. Out there, beyond Jupiter, it suggested something far more provocative: a sender who understood the challenges of interstellar static and tailored their broadcast to cut through it. The real shock, though, was the signal's behavior. After 3 days of uninterrupted transmission, it suddenly shifted frequency, climbing the spectrum in precise 80 MHz steps, almost as if scanning for a response. Then, just as abruptly, it stopped. No fading, no distortion, just silence, as if a switch had been flipped. To this day, the source of signal 12 remains a mystery. No follow-up detections, no debris, no rogue probes spotted by orbital telescopes. Just the haunting realization that something, at least for a moment, was either hiding in our solar system or passing through it. Whether it was a natural phenomenon stretching the bounds of plausibility or something far more deliberate, one truth is inescapable: the cosmos isn't just speaking from the depths. Sometimes it knocks on our front door. The discovery of Signal 12 lurking in our solar system's shadows raises an electrifying question. Could this mysterious broadcast be tied to the interstellar wanderers we've encountered before, objects like Oumuamua? At first glance, the connection seems tenuous. Oumuamua, that bizarre, cigar-shaped visitor, whipped through our solar system back in 2017, while Signal 12 erupted years later from beyond Jupiter. But dig deeper and eerie parallels emerge. Both defy conventional explanation. Both exhibit behaviors that straddle the line between natural and artificial. And both vanish before we can pin them down, leaving behind more questions than answers. Consider the timing. Oumuamua's passage was marked by strange radio bursts and an acceleration that puzzled scientists. Signal 12, meanwhile, appeared years later but shared that same unnerving precision, a modulated transmission that felt engineered rather than chaotic. Could the two be part of a larger pattern? Dr. Avi Loeb, who famously suggested Oumuamua might be artificial, has theorized that interstellar space could be littered with similar objects, some inert, some active, all remnants of a civilization or technology we don't yet understand. If Oumuamua was a scout, could Signal 12 be its counterpart, a relay or beacon left behind waiting to activate. Location adds another layer of intrigue. Oumuamua came from beyond our solar system, a visitor passing through. Signal 12, by contrast, originated within our cosmic neighborhood, yet its source remains invisible. This raises a spine-tingling possibility. What if Oumuamua wasn't alone? What if it was just the first visible piece of a larger, hidden network? Probes, relays, or monitoring stations scattered through the solar system, unnoticed until they chose to reveal themselves. The idea isn't as far-fetched as it sounds. Humanity has already deployed interstellar probes like Voyager, and plans for more advanced missions are underway. An older, more advanced civilization might have done the same, leaving behind artifacts that occasionally wake up, ping their handlers, or even observe us in passing. Then there's the signal structure. Oumuamua's odd shape and motion suggested something beyond a simple rock. Signal 12's circular polarization and frequency-hopping behavior scream intentional design. Both anomalies point toward technology, not geology. Even the signal's sudden shutdown mirrors Oumuamua's own abrupt departure. No lingering, no decay, just a clean exit, as if following some pre-programmed protocol. The symmetry is unsettling. Of course, skepticism is warranted. Space is vast, and coincidence is always a possibility. Dr. Karen Meach, who led Oumuamua's initial observations, cautions against jumping to conclusions. The universe is full of one-offs, she notes. Just because two anomalies exist doesn't mean they're related. Yet even she admits the solar system is still poorly mapped. We've only begun scratching the surface of what might be hiding in the dark, drifting between planets or lurking in the Kuiper belt, the most tantalizing and terrifying implication. If Oumuamua and Signal 12 are connected, their purpose remains a mystery. Are they scientific instruments studying us as dispassionately as we study microbes? Are they relics of a long-dead civilization, their original mission forgotten? Or are they something else entirely, a phenomenon we lack the vocabulary even to describe? For now, all we have are fragments, a strange object that came and went, a signal that flared and fell silent. But together, they sketch the outline of a puzzle far larger than either anomaly alone. The universe might not just be sending us messages, it might be leaving breadcrumbs, hints of a reality far stranger and far more crowded than we've dared to imagine. And the next breadcrumb could be lurking just out of sight, waiting for us to look up at the right moment. Signal 13 arrived like a whisper from the past, a transmission that broke one of astronomy's most fundamental rules. In August 2024, the Mercator Array in South Africa detected a series of radio pulses originating from a faint interstellar asteroid, designated a /2024 G3. At first, the signal seemed unremarkable, brief bursts of static repeating every 94 minutes. But when researchers cross-referenced the data with earlier observations, they caught the anomaly. The pulses weren't just repeating, they were echoing, arriving 3.7 seconds later than they should have based on the asteroid's trajectory and known physics. It was as if the signal had taken a detour through time itself. Time delays in space aren't unheard of. Light and radio waves slow slightly when passing through interstellar plasma or gravitational fields. But the math here was all wrong. Even accounting for every known variable, the density of cosmic dust, the pull of nearby stars, the lag was too long, Dr. Yale Nitsanem at the University of Cape Town ran the numbers and hit a wall. It's like throwing a ball and watching it hang in the air for an extra second before landing, she explained. The universe doesn't work that way unless we're missing something fundamental. Theories erupted, each wilder than the last. One faction proposed the signal had bounced off an unseen structure, a dark matter filament or a primordial black hole too small to detect. Others speculated about slow light effects, where quantum fluctuations in the vacuum of space could temporarily bog down photons. But the most unsettling hypothesis came from Dr. Hiroshi Tanaka at Kyoto University, who suggested the asteroid might be entangled with another object light years away, its signal somehow tunneling through a microscopic wormhole. If even a fraction of the energy was diverted through higher dimensions, he argued, it could explain the delay. Then came the clincher: the echoes weren't static. Each delayed pulse carried subtle distortions, phase shifts, and frequency drifts that mirrored the original signal, but only after it had already arrived. It was as if the universe had recorded the transmission, tweaked it, and played it back on a delay. Dr. Miriam Kubai at the SETI Institute compared it to hearing your own voice in a canyon, only to realize the echo is singing a different tune. The implications ripple far beyond this one asteroid. If signals can be stretched, warped, or rerouted by phenomena we don't yet understand, it forces a humbling admission. Our models of how information travels through space are incomplete. Every interstellar broadcast we've ever detected, every cosmic whisper we've analyzed, might have been filtered through layers of physics we've yet to discover. Signal 13 isn't just a curiosity, it's a crack in the foundation of how we listen to the universe, and the echoes aren't fading. They're asking us to reconsider everything. From Oumuamua's enigmatic acceleration to Signal 13's time-bending echoes, these 25 unexplained transmissions paint a portrait of a cosmos far stranger than we ever imagined. Each signal defies expectations in its own way. Some whisper in mathematical harmony, others scream with deliberate precision, and a few vanish before we can even begin to decode them. Together, they form a mosaic of mysteries that challenges our understanding of physics, intelligence, and our place in the universe. Whether natural phenomena pushing the boundaries of known science or something more profound, these anomalies share one undeniable trait: they refuse to be ignored. The quest for answers is far from over. Every detection rewrites the rules, every theory sparks new debates, and every silent patch of sky begs the question, what are we missing? This isn't just about solving puzzles, it's about rewiring how we listen to the cosmos. The universe isn't a silent void. It's a chorus of whispers, shouts, and echoes, each one a thread in a tapestry we're only beginning to unravel. Now it's your turn. What do you think these signals mean? Are they cosmic coincidences, the fingerprints of advanced civilizations, or something beyond our current comprehension? Drop your wildest theories in the comments. Maybe your idea will be the key to unlocking the next great mystery. And if you're hungry for more deep space enigmas, hit subscribe. The universe isn't done talking, and neither are we.